Ever wondered why elements are placed exactly where they are on the periodic table? At first, it looks like chaos. A jumble of atoms is scattered everywhere. But there's a hidden order, a story written in invisible layers of electrons. In this episode, we'll uncover how electron structure holds the key to unlocking the entire periodic table. You've seen the periodic table, but have you ever asked why it's arranged this way? Each tile represents an element, but this layout isn't random. It's a map of hidden patterns built around two key ideas, periods and groups. Let's break them down and see what your atoms are trying to tell you. Let's start with periods. These are the horizontal rows that run across the periodic table from left to right. There are 7 periods in total. Each period is like a level. Elements in the same row are placed together for a reason we'll explore soon. For now, just remember, when we talk about periods, we're talking about rows. Now let's look at groups. These are the vertical columns that go from top to bottom. There are 18 groups in all. Each group is like a family. Elements in the same group often share similar characteristics. So while periods stretch across and groups fall down, the question is, what's behind this arrangement? The answer isn't on the table, it's inside the atom. Let's take a closer look at how atomic structure helps us understand the periodic table. Here we have 4 elements: helium, oxygen, sodium, and calcium. Notice how their electrons are arranged in orbits or shells around the nucleus. Helium has 1 shell, oxygen has 2, sodium has 3, and calcium has 4. We can also write this arrangement using electron distribution by shell. Helium is 2, meaning 2 electrons in the first shell. Oxygen is 2, 6, 2 electrons in the first, 6 in the second. Sodium is 2, 8, 1, 2 in the first, 8 in the second, and 1 electron in the outermost shell. Calcium is 2, 8, 8, 2, showing 4 occupied shells. This shorthand makes it easier to see patterns, and it's just as informative as the full diagrams. Now let's see where these elements are on the periodic table. Helium is in period 1, oxygen in period 2, sodium in period 3, and calcium in period 4. Notice the pattern? The period number matches the number of shells in the atom. So if an atom has 3 shells, you'll find it in period 3. Simple as that. Here's period 4 highlighted on the table. Each of these 18 elements has 4 shells or energy levels. That's what it means to be in period 4. Here's period 5. All these elements have 5 shells. That's why they're in period 5. The 6th period, one of the longest rows in the periodic table. Notice how it stretches way below. Yes, these lanthanoids, along with the actinoids beneath them, are actually part of the 6th and 7th periods. We now know that the row or period tells us how many shells an atom has. But what about the columns? Why are elements stacked this way? Let's look at these 4 elements again, but this time we'll focus on the valence electrons, the ones in the outermost shell. These outer electrons play a big role in how atoms behave. Helium has 2 electrons, both in its only shell. Oxygen has 6 in its second shell. Sodium has 1 in its third shell, and calcium has 2 in its fourth shell. Take a look at the shell notation. The last number tells us how many valence electrons are present. And that's exactly what the vertical columns on the periodic table, the groups, are all about. Now let's locate them on the periodic table again. Notice where each one falls. Helium is in group 18, oxygen in group 16, sodium in group 1, and calcium in group 2. Let's uncover what these vertical columns or groups are really telling us. Let's start with group 1, the first vertical column on the left. These elements are known as the alkali metals, except for hydrogen. Hydrogen isn't a metal, but it's placed here because it also has 1 valence electron just like the rest. That single outer electron links them together and gives them some similar behaviors. Next is group 2 right next to it. These are the alkaline earth metals and they all have 2 valence electrons. So just like calcium, the rest of this group shares the same outer electron count. Now let's move to groups 13 to 18. Each of these groups has elements with the same number of valence electrons just like the earlier ones. Group 13, called the boron group, has 3 valence electrons. Group 14, the carbon group, has 4 valence electrons. Group 15 is known as the nitrogen group. It has 5 valence electrons. Group 16, the oxygen group, has 6 valence electrons. And group 17 is called the halogens. These elements have 7 valence electrons and are very reactive, especially with elements from group 1. Notice the pattern? The last digit of the group number matches the number of valence electrons. Group 13 elements have 3 valence electrons, group 14 have 4, and so on. Now let's look at group 18, the noble gases. These elements are known for being very stable. Why? Because their outermost shells are full. For most of them, that means 8 valence electrons. A full outer shell makes them unreactive. They don't need to gain or lose electrons. But wait, what about helium? It's in group 18 too, but it only has 2 electrons. That's because it has just 1 shell, and 2 electrons is enough to fill it. So even though it doesn't have 8 like the others, each shell is complete, which makes it just as stable. That's why helium belongs here with the noble gases. Let's take a step back and see the bigger picture. Here we highlight the main groups, groups 1, 2, and 13 to 18. These are the groups where the number of valence electrons follows a clear and consistent pattern, and that makes them especially important for understanding how elements behave. So main group elements follow a pattern, but what about those in the middle, groups 3 to 12? Or the 2 rows floating below the table? Let's uncover those exceptions next. First, we have the transition elements, groups 3 to 12 in the middle block. Their electron configurations are more complex, and that's why they don't follow the simple group valence pattern we saw earlier. Next, look at elements 109 to 118. Some of them sit in the main group columns, but many are synthetic and not much is known about their reactivity or valence patterns. Still, based on their placement, scientists predict they behave much like the other elements in their group. And finally, we have the F-block elements, the lanthanides and actinides. Like the transition metals, they also don't follow simple group valence rules and are usually studied more closely in advanced chemistry. So while the main groups follow clear valence patterns, exceptions like this remind us that the periodic table has its quirks. Now that we have explored the structure, the periods, the groups, and even these special cases, it's your turn to spot the patterns. Ready for a quick challenge? Let's dive in. Let's try this. Where would you place the element with the electron configuration 28 in the modern periodic table? Is it A, group 2, B, group 8, C, group 10, or D, group 18? The correct answer is D, group 18. Why? Because 28 means the outer shell has 8 electrons, a full stable shell. And that's the defining feature of group 18, the noble gases. Next, which of the following represents an atom from period 3? Look closely at each atom's electron structure. The correct answer is B. Remember, the period number tells us how many electron shells are occupied in the atom. Next, which 2 of the following electronic configurations belong to the same group in the periodic table? Remember, elements in the same group have the same number of valence electrons, those in the outermost shell. So which 2 configurations match? The correct answer is A and D. Configuration 21 and 281 both have 1 valence electron even though they're in different shells. That puts them together in group 1. It's the valence electron count that matters most. Let's test your periodic table instincts. Which of the following pairs of elements are most likely to have similar properties? Is it A, hydrogen and helium, B, beryllium and strontium, C, sodium and magnesium, or D, boron and oxygen? Remember, the key clue lies in their placement on the periodic table. So which pair shares the same group and therefore similar chemical properties? The answer is B, beryllium and strontium. Both are in group 2, the alkaline earth metals. Even though they sit in different periods, their group connection means they behave in similar ways. Here's your next clue-based challenge. An atom of a main group element has one electron in the outermost fourth shell. State its atomic number, number of protons, electronic configuration, valency, and the element name. So we know one electron in the fourth shell. Assuming it's a main group element, can you figure out which element it is? If you got a periodic table nearby, you can use it. But let's challenge ourselves to solve it without one. We'll use this blank table instead and track those clues visually. Remember, the number of shells tells us the period and the number of outermost electrons tells us the group. So, one electron in the fourth shell means period 4. And since there's only one valence electron, that places it in group 1. Where period 4 and group 1 meet, that's our mystery element. It leaves us right here. To find its atomic number, we'll count each elementile one by one starting all the way from hydrogen. Watch as the number climbs until it lands here, 19. So for A, atomic number, the answer is 19. For B, number of protons, it's also 19. Why? Because the atomic number tells us the exact number of protons in the nucleus of an atom. It's like the element's ID number, unique and unchanging. So if the atomic number is 19, the atom has 19 protons, no more, no less. Now let's figure out the electron configuration of this element. We'll use a simple shortcut that works for the first 20 elements, the 288 rule. Period 1 can hold only 2 electrons, and notice the first row of the periodic table only has 2 elements. Period 2 can fit up to 8 electrons, and sure enough, the second row has 8 elements. Period 3 also fit 8 electrons, and again, the third row has exactly 8 elements. So after filling periods 1, 2, and 3, we've used up 18 electrons. That leaves us just 1 electron for the fourth shell, which means the configuration is 2881. This shows us exactly how electrons are arranged and confirms it's in period 4 with 1 valence electron. The problem tells us this atom has 1 electron in its outermost shell, and that's all we need to figure out its valency. Valency is simply the number of electrons in the outermost shell, and in many cases, it matches the element's group number. So since this atom has 1 outer electron, its valency is 1. That's why it belongs in group 1 on the periodic table. Elements in this group all have 1 valence electron and show similar chemical behavior. Now let's figure out the name of this element. Remember the first 20 elements mnemonic we learned in the last episode? Let's walk through it together, count along. Harry helped Lily be brave, Cat snap on fluffy neckties, Naomi's magical aluminum sink pops, and Sassy Clown argues with King Carl. That brings us to element number 19, symbol K, for potassium. So the element with atomic number 19, 1 valence electron, and 4 shells is potassium. Today we uncovered how the periodic table's structure is built on electron arrangements. Shells tells us the period, valence electrons tells us the group. We explored the main groups, the exceptions, and used that knowledge to place real elements. The periodic table isn't just a chart, it's a map written in electron clues. Next time, we'll see how those outer electrons drive reactivity, why some atoms react wildly while others hardly react at all. Thanks for watching, and I'll see you in the next lesson.